Hi, welcome back to a video series on MAC 1140 Precalculus Algebra. This is the guided notes number 2 in the series on section 1.2, factoring polynomials. So these three ask us to factor out the greatest common factor of the polynomials below. So the greatest common factor is going to be the number, the monomial, which can be divided from every term, and it will be the largest such monomial. We want to look at the coefficients and ask what their greatest common factor is, and then we'll look at the variables part separately. So the coefficients are 5, 15, and 10 for this one. The greatest number I can divide into all of them is 5. So when we factor this, we're going to pull a 5 out, and something will remain. Now, the greatest variable term, the one with the largest exponent that I can divide from everything, is actually going to be the smallest exponent. So scanning through here, we see that the smallest power of x is the square, and we're going to divide that from every term. We're going to actually divide this whole monomial 5x squared from every term. So if I do that here, the 5 cancels to 1, and dividing out x squared from this would give me x to the third. Remember, we are looking at the difference of exponents when we divide like bases. Then dividing 5 from this, I get 3. Dividing x squared from it, I get 1. Dividing 5 from this, I get 2. And dividing x squared, I get 1. So this is just a 2. And there you have it. Let's repeat that for each one. Looking through at 21, 3, and 3, I wind up with the greatest common factor of 3, so we can pull that out. Looking through at x's, I have x to the fourth, x to the third, and x squared. The largest thing I could divide out is x squared, the smallest power. And looking at the y term, looking at the y part of the term, I could divide out y to the fourth. Y to the fourth is the smallest of these three, and so it's the thing that I could divide from each one without having some kind of rational term remaining. The greatest common factor is actually one of those problems that you could ask that's simple enough that we could ask it for a two-variable polynomial like the one shown here. We haven't really defined two-variable polynomials yet, but suffice it to say, it's got two variables, but the same rules of powers apply. No negatives, no fractions, only non-negative integers. So let's divide this monomial term 3x squared y to the fourth from each term. Dividing from 21, I get 7. Dividing out x squared, I get another x squared. And dividing out 4 y's, we get a single y remaining. Plus, dividing by 3, we get 1. Dividing by x squared, we get x. And dividing by y to the fourth, we get y squared. Finally, we have dividing by 3, we get 1. Dividing by x squared, we get 1. And dividing by y to the fourth, we get 1. Okay, so everything canceled there, but we have to be careful that we cancel to 1 because we're canceling by division. If you were to FOIL this back into each term, you would need to get the line that you started with. So the only way to do that is to put a 1 here to hold place. Last one, the greatest common factor of 15 and 6 is 3, and the smallest exponent here would be x squared. Dividing 3 out of this, we get 5. Dividing out x squared, we get a single x. Dividing out 3, we get 2, and dividing out x squared, we get 1, so that closes. The following three problems ask us to factor these polynomials by grouping. Factoring by grouping is a nice technique when you have 4 terms. Recall, we're going to want to cut this in half and factor each one separately using the greatest common factor. Factoring here, I can pull out a y squared, which leaves me with a y and a 6 remaining. Factoring the greatest common factor here, I could pull out a 2, which leaves me a y and a 6 remaining. So the way that we know that factoring by grouping is going to work is if I have repetition of a term inside these parentheses here, you can see both of them have a y plus 6. So we could factor that out as well. Factoring out the y plus 6, we wind up with y squared plus 2 times a single y plus 6. And this is factored. Let's repeat. Dividing this one in half, we can pull out an a from each one of these terms, which would leave me x minus 3. We could pull a 7 out from each one of these terms, which would leave me x minus 3. Because we have a repeated x minus 3, we could divide that out as well, and that's going to leave us with a plus 7. So here we have the factored form. Finally, we have one where this polynomial could be combined with like terms to give me a trinomial. So technically, we've sort of unsimplified this, but a common technique of factoring is to simplify your middle term so that you can factor by grouping. So cutting this one in half, we have a w squared we could pull out of everything. We have a minus 4 that we could pull out of both of these. And that would leave us with a single w here and a positive 2 here. Remember, dividing by a negative divided by a negative is going to give us a positive. And on this side, if I also take out a negative, looking at this side, we could take out a minus 14w from each one. That's going to leave me a w plus 2 here as well. So we could complete this by factoring out the w plus 2. We'll write it in the front or behind. And that's going to be minus 4w squared minus 14w. Now there's something I'd like to do to sort of clean up that last answer, because this thing is not completely factored in terms of a greatest common factor. Actually, a w could be brought out of both terms, and so could a minus 2. So let's pull that way up front and say this is minus 2w, w plus 2 as a second multiplicative term. We would now have 2w plus 7. This is now completely simplified. So in this next problem, we want to look at the difference of squares formula. Let's remember that if we have a difference of two terms squared, this could be factored as the sum of their roots times the difference of their roots. Take the square root of one term, the square root of the other term, and that would give me a and b here. So we really want to see what is our a and what is our b. Well, here, the thing being squared could be seen as 2x squared, and this is, of course, 9 squared. And that tells me that I could rewrite this as 2x minus 9, or plus 9, times 2x minus 9. It doesn't really matter if we put the plus or minus first. It only matters that we get both of those, positive term and a negative term here. Here we have another example. Is 576 a square? That's the question. Well, maybe you don't have all of your squares memorized up to 576, but we could just take the square root, or the 1/2 power, and find out that that is 24 squared. So rewriting this, we have this is 2r squared minus 24 squared. In other words, we could factor as 2r plus 24, 2r minus 24. And you might notice that this is not completely reduced. We could reduce these by factoring a 2 out of each one, which puts a 4 up front, and then we would have r plus 12 and r minus 12. And that's actually an indicator that we could have simplified this a bit more at the beginning. Notice that I could have rewritten this right from the get-go as 4 times r squared minus 144. We can check that 4 times 144 actually gives me 576. But then we could factor straight away and wind up with the same answer. Here we have another difference of squares. It is in fact a square. It is 25x squared squared. The square of a square will give me this 4th power. And this one here, this is actually 2 to the 8. So 2 to the 4, or 16, will square to give me 256. And y squared is what we're looking for here. So let's write this using the difference of squares formula. We would have 25x squared plus 16y squared times 25x squared minus 16y squared. But then you probably notice that this now is also a difference of squares. So let's move this over and continue our factoring by factoring this second term, which is now also a difference of squares, 25x squared plus 16y squared, and the second term factors as 5x plus 4y times 5x minus 4y. So not just one application, but 2 applications of the difference of squares formula were possible. So the next two want us to use the sum and difference of cubes formula to factor these 2 polynomials. Let's either learn or recall the definition for the difference of cubes formula. To write it in its most compact way, if I have any 2 cubes, whether that's a sum or a difference, then this can be factored in the following way. I could take either a plus or minus b. Notice this sign matches in this first term, times a squared minus or plus, so we change the sign here, ab, and then this one is always a plus, b squared. So this is just an easy way of writing the 2 formulas as one formula, and it reminds me of a way to memorize it. If I have a plus here, this one will be a plus, and this one will be a minus, and this one is always a plus. If I have a minus here, likewise, this leading term will be minus, and this one will be a plus, pluses all the way down. So this one here is just sort of a shorthand for writing both of these two here. Now, we need to see what are our cubes, and then we need to sort of plug them into these equations. If you want to verify that they work, just like verifying that the difference of squares formula works, you could FOIL, or expand, I should say, each one of these and confirm that the appropriate cancellations happen and that you just get the sum or difference of cubes. So with this one, we actually have y cubed plus 5 cubed. And this tells me I'm going to be looking at y plus 5, and then we do y squared minus 5y plus 25. This one, 2 is not a cube, nor is 16. But if I factor out the 2, then I wind up with a difference of cubes. 8 is 2 cubed. And so we could think about this as 2 times y minus 2 times y squared plus 2y plus 4. And that's really all that's necessary for doing sum and difference of cubes formulas. You have to have this formula on deck, and then you find out which your cubes are and plug them in appropriately. Here we're just asked to factor some trinomials completely, so let's do that. They're monic trinomials, which is what we say when the leading coefficient is 1. And if the leading coefficient is 1, these are usually a bit simpler to factor. I have the following pattern that I follow. I set up my parentheses, and then I fix my signs. There's at least one negative sign, because this is negative, and a negative times what will give me a negative times a positive. There needs to be an x in each place to give me an x squared up front. And now I'm looking for two factors which will multiply to be 5 and have a different signs difference of 4. That's, of course, 5 and 1. And if you drop this sign straight down, you can always put your larger of the two factors, the larger in magnitude, in that position, this first position here. Let's do that again. So this one says we have a y and a y. I have pluses all around. Plus times a plus gives me a plus. And then we need factors of 32 with a same sign sum of 12. So factors of 32, we're going to have 32 and 1. We're going to have 16 and 2. We're going to have 8 and 4. There it is. So we put 8 and 4, and we're done. Here we have a two-variable polynomial, and two-variable polynomials are generally a bit trickier, but that tells us that there must be some trick to doing this, because they couldn't ask me about factoring two-variable polynomials in general. Let's just go along with this pattern. We know it's monic, and so we could put an x and an x in each position. We have a minus sign here, so there's at least one minus, and a minus times something will give me a plus. A minus times another minus gives me a plus. Now, we know that we're going to need two y's here, but we also need two numbers that will multiply to be 40 and have a same sign sum of 14. Thinking about it for a second, that's 10 and 4. And did this work? Sure did. Negative 10xy, negative 4xy. This would give us negative 14xy in the middle. So there is our factored polynomial. This one isn't monic, or is it? Notice that a 4 could go into each term. You should always try dividing out the greatest common factor first before you attempt to factor any polynomial. The greatest common factor is an easy way of seeing whether or not something can be simplified before we begin, and it's easier to work with smaller numbers. So we set up our two parentheses. We have a monic, so this is x and x. We put a plus here and a plus here, and factors of 27 with a sum of 12 are 9 and 3. We're done. Same notion here. We could factor out a greatest common factor, which is going to be 8. And in fact, 8y squared could we pull out. So let's write 8y squared here. This would give me a y squared in this position, minus 12y, and this would be plus 20 alone. So factoring this will have us putting a y in each position, a minus here, and then another minus so that we multiply to get this positive. Factors of 20 with a sum of 12 are going to be 10 and 2. Here I have a non-monic polynomial. It's got a leading coefficient of 2, and there's no way to divide 2 out of the other terms. So what we'll need to do is sort of confront that. Now, there are a variety of different methods. I use a variant of the AC method to do this, because I want to set up my parentheses again. I know I'll need at least an x and an x. I know I need at least a plus and a plus. And now we need to fill in these 4 spaces with numbers. It's sort of easy to guess and check when they're both prime, but it's not going to be quite as easy when we have larger numbers, especially if they're composite numbers with a lot of factors. So let me show you what I would do in general. I would actually put a 2 here and a 2 here to avoid having to answer the question of where my 2 should go. Now that's of course timesing an extra 2 inside, so I balance it with a 1/2. Before you freak out, just notice that this would be 4x squared, but half of that would be 2x squared. So nothing's wrong yet. We haven't written down anything wrong, and in fact, it's going to be balanced with the line above. However, there was a cost to filling this in. So now I only have 2 spaces left, but there was a cost to that, and it was multiplying by an extra 2. This tells me I'm not looking at factors of 3, but factors of 2 times 3. That's why this is called the AC method, because we use the A and C coefficients and take their product and look at its list of factors. So this is 6 and 1, or 3 and 2. And 3 and 2 actually have the sum of 5. 6 and 1 have a difference of 5, but we see because these signs are the same, we're looking for a sum of 5, which is going to be 3 and 2. Finally, we reduce our answer. Notice that this one has a greatest common factor of 2. That can be pulled out. But wait, where did it go, right? Okay, well, there's a 1/2 waiting for it up front. So we pull out a 2, but then 1/2 times 2 is just 1, and it goes away. That'll happen every time you use this method, and I find that pretty satisfying. Let's see what we can do with the remainder of these. So looking for greatest common factors, I have a 3 that could be pulled out of each one, and that would leave me with 15z squared plus 17z minus 4. 15, 17, and 4 have no common factors, so we continue from here. Again, my preferred method is to set up my parentheses, put a 15z in each position, and a 1/15 up front for balance. Resist the urge to cancel it with this 3. Then we have a plus and a minus to fill in my signs correctly. We take the product of 15 times 4 to give me 60, and 60, we look through the factor list of 60 for numbers, factors of 60 that have a difference, because these are different signs, difference of 17. So 2 and 30, or 3 and 20, and there it is. If you drop this sign down, you can simply put your larger number first here, and then our 3, and now we are going to factor out what remains. So we still have this 3 up front. If I factor out a 5 from this, I'll have 3z plus 4. And if I factor out a 3 from this, I'll have 5z minus 1. And the 5 and the 3 together canceled with the 15, and we are done. Let's do another one of this kind. I notice a 3 could be pulled out of everything, so let's do that first. In fact, not just a 3, but a 3w. So this would give me 6w squared plus 11w plus 3. Now we want to set up our parens. I will put a 1/6 up front, a 6w here, a 6w here, and then plus and plus should be our signs. 6 times 3 is 18, and we look through our list of factors of 18 for ones with a sum of 11, which is 9 and 2. Put a 9 here and a 2 here, and then we will factor out their greatest common factor and reduce. Pulling out a 3, pulling out a 2, we cancel with the 6, and then we have 2w plus 3 and 3w plus 1. And that's all there is to that one. So here we have some applications of these. We want to solve equations that have polynomials inside. Now, the main idea here is that we can't simply start attacking this with inverse operations. What we need is to take advantage of the zero product property. The zero product property says if I have 2 numbers in product equal to 0, well, surely if one of them is equal to 0, then their product will be equal to 0. But what's actually true is this is a biconditional. That is to say, if A times B is equal to 0, the only way that happens is if one of them is 0. So factoring something once it's been set equal to 0 can reduce the equation by quite a bit. Now you have 2 separate but simpler equations. So let's see how we would do that here. So let's begin by subtracting everything over to the other side. We have minus 14m then, and plus 33. And that's going to be equal to 0. We factor, set up our parens, m and m, a minus and a minus times a minus will give me this plus. Factors of 33 with a sum of 14 are 11 and 3. Now, because this product is equal to 0, we know that either m minus 11 is equal to 0, or m minus 3 is equal to 0. In one case, we would get positive 11. In the other case, we would get positive 3 as our values for m. So So these are our two solutions. Here we have one that's already set equal to 0. If I factor out the x from each of these two terms, I wind up with x squared minus 100, which is a difference of squares. So that could be factored as x plus 10 times x minus 10. Setting each one of these three terms equal to 0, we will wind up with solutions of either x equals 0 from the first one, x equals minus 10 from this one, or x equals positive 10 from the last factor. So this is a method called completing the square. The way that completing the square works is by making the following observation. If I were to have some polynomial a plus b and I were to square it, what I would wind up with in the middle is going to be 2 times the product of what's at the end. 2 times the product of these two terms inside of the parentheses. And so if I would like to get some single thing, what I could think about is, what about, for example, x plus a half of something? Let's say d over 2. What would happen if I were to square that? Well, we'll get x squared. We'll actually just get a single d times x, and then at the end we'll get something else. We'll get d squared over 4, or better yet, how about just d over 2 squared? So the idea is that if I am given this part, the x squared and the linear term dx, then what I would like to add in order to make that factor is d over 2 squared. So d over 2 squared in this case is going to be what we're going to add. So notice here, what's playing the role of d? Minus 11. So what we would want to add is minus 11 over 2 squared, which is going to be 121 over 4. If we add that to this equation, then what we would get is the following. We have t squared minus 11t. I'm going to add to that 121 over 4. But then we can't just go around adding things willy-nilly. I also need to take that away so that I've truly just added nothing. This whole part here is just 0, so it's like we didn't really do anything if I add and subtract it. But now that we've added this special number, this first part factors as a perfect square. That is to say, just something, x plus something squared. That something is the half of 11, the thing playing the role of d over 2 here. So that's going to be t minus 11 over 2 squared minus 121 over 4. And you might think that's not such a great improvement, but actually it's great if we have a perfect square, because then we really can just use inverse operations to solve equations that have, like, say, for example, if this had been set equal to 0. We would just move the 121 over 4 over and then take plus and minus the square root of each side. And it's actually completing the square that we would do if we wanted to generate the quadratic equation. But let's just apply this as sort of an algorithm. What do? You look at the term that's next to the z, and then you would add minus 18 over 2 times 19, half of this, which would be 38, and then you square it. Now, rather than do this all the way out like I did with the 11, I'm just going to leave this as is. If I took z squared minus 18 over 19z, and then to this equation, I were to add minus 18 over 38 squared and subtract minus 18 over 38 squared, what I would wind up with in the first position is a perfect square minus z minus 18 over 38 squared, and then this, so that's all this part here, turns into this perfect square. And then remaining on the outside, we have minus 18 over 38 squared. Actually, rather than just linking you to the video, I'll just derive the quadratic equation right here. If I have ax squared plus bx plus c is equal to 0, if I divide everything by a, I wind up with the following. And then if I move c over a to the other side, I will wind up with minus c over a. And then what I would like to add to this to make it a perfect square is half this term squared. So that would be b over 2a squared. And I'm going to need to do this to both sides in order to keep balance. Now, on my right-hand side, I'm going to wind up with the perfect square, x plus b over 2a squared. And over on this side, well, let's square this. We have minus c over a plus b squared over 4a squared. In order to get these fractions the same, what I would like to do is multiply this fraction here by what this one has that it's missing in the base, which is going to be a 4a in both places. So what will that leave us? Well, on the bottom here, I'm going to have 4a squared. On the top, I'm going to have b squared minus 4ac. And maybe you're already starting to see it. Now we want to use the square root property. This is actually the advantage of difference of squares, is now that we have a perfect square, we know that x plus b over 2a, this is going to be equal to the square root, plus and minus, of b squared minus 4ac over 4a squared. But we can actually take the square root of 4a squared. That's just 2a. And we're so close to done, right? If I bring this over, I have minus b over 2a plus and minus the square root of b squared minus 4ac over 2a. And last but not least, we just combine our like-based fractions over here to get x is equal to negative b plus and minus the square root of b squared minus 4ac over 2a. And there's your quadratic equation. So not a terrible derivation if you understand how to complete the square. Namely, the whole trick of this was to add half of this middle term squared to both sides. After that, this is a perfect square trinomial. Then we just do some fraction math over here, square root property, bada boom, bada bing, we get the quadratic equation. Thank you very much for your patience. Have a great day. Good luck with your studies, and I will see you in the next one.